Hello, this lecture is on light emission and absorption and an important process called the photoelectric effect. So the first question we have to answer is, where does light come from? If you wanted to get or create a new piece of light, what processes would you have to undergo to get it? Well, because mass energy together are conserved, we can get new light either from a transformation of existing energies, chemical energy, nuclear energy, electrical potential energy, or you can get new light from a loss of mass somewhere. So the sun is an example of transforming, generally speaking, nuclear energy into light. Also, there's some mass being converted into light as well. Light bulbs are transforming electrical energy into light. And these are some examples of burning different chemicals, which may happen in your chemistry classes. And in those cases, we're taking chemical energy and turning them into light. A note, you can reverse this process as well, which means that you can take some light that's out there and turn it back into these other kinds of forms. You can take light and turn it into chemical energy or electrical energy, or you can take light and turn it into mass in theory as well. So with all of that being said, the two most common and important in terms of this class light generating processes are known as blackbody radiation and electron orbital transition. So blackbody radiation is actually a spontaneous process that happens in every object, everything with mass, that includes you, in the entire universe. Over time, we'll be converting internal energy in those objects, or thermal energy, into light. This is an example of a photograph of a person with a camera that sees in the infrared spectrum. And you can see that that person is actually emitting light photons. They're infrared light photons, not visible light photons. So in a dark room, we don't see them, but a camera can detect those photons. And that's as a function of that person's thermal or heat energy in their body being transformed into light photons. This, incidentally, is a requirement of the second law of thermodynamics, which is that entropy in the universe must always be increasing. And at the core, this is the reason why it happens. Every object actually produces a bell curve of light frequencies, which means that even though that person there is mostly sort of emitting these infrared photons, they are emitting technically some visible light and some gamma and all those other kinds of photons as well. But the peak of the bell depends on the object's average temperature. So for a person, for example, well, I guess I should start by saying the sun for us appears yellow because the temperature of the sun is somewhere around, it looks like about 400 Kelvin right here. So you can see for a 400 Kelvin object, the peak, or the top of the peak, is in the yellow range. So that is a way of determining actually the temperature of objects, is by what color light is the primary light that they emit. Human black bodies have a peak way out here in the infrared range, right? So this is down in the this is 3,000 Kelvin. You can imagine that if we are down with us, which is somewhere in the less than 1,000 Kelvin, right? The peak is way out here. So the bulk of our black body emissions are going to be infrared. The second primary way in which we create new light photons is through electron orbital transition. We've mentioned bound and free as terms before when we were talking a little bit in our electrostatics unit, but in general, bound electrons are ones that exist inside the orbital of an atom. And there is a rule in chemistry that says those electrons must exist in and only in these discrete orbitals. So there's these specific levels or layers, and this is an old model of an atom, but it works for this purpose. And the idea is the electrons can be at those layers, and they only at the layers. They cannot exist. I can't have an electron that exists there in between orbital levels. Okay, they can only exist on those discrete shells. That being said, electrons can move from one to another. It's kind of this tricky process where they move from one to the other without existing at any space in between. But in any case, electrons can do that. And in the process of moving from one orbital level to the other, or from moving, you know, that way, either direction, energy can be absorbed or released, and often that energy is in the form of new light photons. So in physics, we make these things called energy level diagrams to talk about what is happening as electrons bounce around between those orbital levels. You can picture this as kind of a cross section, like a little piece of that orbital diagram that we saw in the last slide. In that diagram, every possible orbital that the electrons can exist in is given an n value, starting with the one closest to the nucleus, which is n equals 1. And each orbital also has a characteristic voltage. And if you remember voltage is defined as electrical energy per unit charge. So if you take that voltage, which is not shown in this picture, and you multiply it by the charge of a single electron, which is negative 1.6 times 10 to the negative 19th, okay, from your equation sheet. So if you take the voltage multiplied by the unit charge, then you get the energy of an electron located at that location. And that's called an energy level. And so these diagrams actually show how much energy would an electron, a single electron, have if they were located in each one of these orbitals. Incidentally, these electrons, these energies are measured in electron volts because obviously we're dealing at that kind of scale. And a reminder that 1 electron volt is defined as 1.6 times 10 to the negative 19th joules. The orbital n equals 1, which I've highlighted already, is known as the ground state, and it is the lowest energy configuration for the electron. You know, you can imagine the nucleus being down here somewhere, and so if you're an electron located in the ground state, you are as close to the nucleus as you can possibly be. That is a low energy level because it goes there spontaneously. You'd have to do work to push it further away. This is a negative energy value just because of the way that last equation worked out, right? We have that equation of voltage equals energy per charge. And so since that charge was negative and the voltage was positive, the energy values that you calculate end up being negative as well, just based on the math of the way they end up. So this is a negative energy value. And it is the lowest energy configuration. As you move further away from the nucleus and you have that electron move, or imagine an electron that exists in different orbitals, different levels, we call them the excited states. So the first excited state is like not the closest level, but one level out, and then second, third, fourth, etc. as you move further. And those levels are going to be called higher energy orbitals because electrons that exist in those excited states have more energy than the electrons in the ground states because they are further away from the nucleus and work had to be done to move them there. The last level is known as an ionized state, or sometimes this is called ejected. And this is what happens when an electron actually gets booted out completely from that atom. And that can happen on occasion. We can have electrons lose, or atoms lose their electrons. Technically, this ionization state is infinite distance from the nucleus in all practicality, right? As soon as you get, any kind of finite, atoms are really, really small. So infinity happens actually, you don't have to be that far away before you're essentially at this state. And if you remember that we defined voltage of 0 at infinity, that may make sense why this energy level is 0 electron volts, because if that voltage is 0 in the equation, no matter what you multiply the Q by, the E has to be 0 as well. So that ionization state is a 0 electron volt energy level, but it's actually the largest n equals infinity at this location. So it is the furthest possible location from the atom. Okay, so if you have this atom with an electron that currently is located in the ground state, electrons are going to tend to gravitate by themselves to those ground states. They want to be as close as possible to the nucleus. and it gets hit by a photon of light, that electron may absorb the energy of the photon and use that energy to jump up to the next energy level. Okay. Now notice that I use the word may. That's important because it only does this in a couple very specific instances. The only time it can do this is, number one, if we absorb a photon that has exactly the right amount of energy to put me into a new orbital. Because the electrons have to absorb photons whole, you can't break a photon into pieces, I have to use all of the energy of the photon somewhere. And if all of the energy of the photon doesn't put me exactly in one of those energy orbital levels, then I can't absorb it at all. So we can absorb photons that have exactly the right amount of energy to put me into a new orbital. So if I'm starting at, at this ground level, I can absorb this red photon that puts me up here into N2. I can absorb a green photon that puts me here. I can absorb a blue photon that puts me here, but you'll notice that there's no yellow, right? The yellow would exist somewhere in here, okay? And there is no possible energy level for me there, so that means that, I can't absorb that yellow photon at all. The other choice is that you could absorb enough energy to ionize. So if I have a really, really, really high energy photon that comes in, and that is enough energy to send me all the way to the n equals infinity state, or more, then that's fine. I can absorb that. I can absorb the highest energy to infinity plus any energy more than that. So all other photons, like the yellow ones I mentioned, the atom is what's called transparent for those photons. They actually just pass right through. So if I had this yellow photon coming in, it's just going to go right through that electron. The electron's not going to touch it at all, and it's just going to pass right through the atom. It's transparent, whereas that red one gets absorbed because it's got the right energy to send that electron directly to another energy level. So a common problem that comes up on the AP exam is for you to calculate what frequencies of light would be absorbed. So imagine an atom being irradiated or hit with light. What are the frequencies that this particular atom with this electron level diagram would absorb? And so maybe you'd get a question, what are the lowest 3 frequencies of photons that are absorbed by the atom shown in the energy diagram to the right? So I would recommend pause this video, see if you can solve this whole problem, and then unpause it and see what my solution is. So the steps that I would take, I would start by assuming my electrons start in the ground state. And then I would calculate delta energy to each excited state. So for example, on this first one, I would say, my final state is negative 30.6 minus my negative 122.4 to find out exactly how much energy we would have to absorb to go from the ground state to the first excited state. Then I would use the Planck's photon energy equation to calculate the frequency of the photon that has exactly that amount of energy. That equation again is E equals HF, okay? So we have the energy that we just calculated. That's going to go in here. H is a constant. Because my energy is measured in electron volts, make sure you use the constant that is in EV, and that should allow you to calculate the frequency. Incidentally, you might also be asked to figure out what is the wavelength of this photon. If you were doing that, you would use the wave equation. So lambda equals velocity, which in this case is the speed of light, divided by the frequency that you find, and that would allow you to get wavelength. You might also be asked to figure out what color this is. You would have to use your electromagnetic spectrum to know what color that was going to be. So the solutions I got, which I've written over apparently, are 2.21 times 10 to the negative, or 10 to the 16th, 2.47 times 10 to the 16th, and 2.6 times 10 to the 16th hertz. So those are the photons that would send me from ground state to 1, ground state to 2, and ground state to 3. So a related question would be to ask you to analyze or understand what's called an absorption spectra or spectrum. So if you have a pure sample of some kind of atom and you shine a white light through the sample, the light that gets to the other side is going to have gaps in it. It's going to have gaps at whatever frequencies are being absorbed by that gas. And this graph or this diagram is characteristic of the gas sample atom, and it's actually the way that we made the energy level diagrams in the first place. We basically did the reverse process of the last slide. First, we figured out what frequencies were missing from our white, and then we can figure out what the energy diagram should look like. So for example, if you have a sample of hydrogen gas and you shine white light through it, what you get is on the other side of the hydrogen gas, you see most of the colors of the white are transparent, pass right through, but there's these little gaps right here, okay? These black lines are basically showing frequencies of light or colors that are being absorbed by the hydrogen gas. So those are like the magic colors that happen to have exactly the right energy to bump the electrons in the hydrogen gas up to specific energy levels. So if we have this picture, we can then figure out what our energy level diagram should look like from that picture. This is actually a really, really useful process, and astronomers use this to learn about what is in between us and stars. So we know what this, by the way, is sort of like a black body spectrum. You can see that shape, right? White light shape of that spectrum. So we have the black body spectrum of the stars in space, and we know what that spectrum should look like based on the composition. We can figure out the composition of the stars. And then as that gas tries to get to us on Earth, it passes through other dust and things that we can't see in space. And what we notice is some of the colors get absorbed. So we can figure out what's in between us and the stars based on the energy levels that are being absorbed by the gas in between us and the stars. So it's a pretty cool process. Okay, so the opposite process from photon absorption is called photon emission. And photon emission happens when an atom contains an electron that's already been excited, so it isn't in the ground state, it's already starts up in an energy level further away from the nucleus. And over time, that electron is going to spontaneously decide to fall back to the nucleus in the ground state because opposite charges are going to be attracting. And when it does that, of course, it has to release its energy somewhere. And usually that energy is released or emitted in the form of new photons that are created out of that energy that is lost when the electron moves back. Just like with the absorption, the frequency of the emitted photons is going to be the frequency that provides exactly as much energy as those electrons are going to lose when they change energy levels. There is one difference in between absorption and emission when you look at the energy level diagrams, and that is that when you are absorbing photons, because you have to absorb the entire photon in one gulp, and because electrons always start in the ground state, there's only a few options. Like here we've got this 1 electron volt photon we can absorb, or the 3.0 electron volt photon that we can absorb. But since we're always starting here, those are the only two choices. Emission is a little bit different because when electrons start in an excited state, sometimes they go all the way back down to the ground state in one jump. But other times we see that those electrons actually stop briefly at energy levels on the way. Okay, that never happens with absorption. You can't stop at an energy level and then absorb more from there. You have to go all the way up in one shot. But on emission, you can stop on the way. And so that means that there are more different possible photons that can be emitted than can be absorbed, right? There's only 2 photons that will cause that ground state electron to jump up, those green ones, but there are 3 photons that would be emitted when an electron starts up here in 3 electron volts. There's 3 different colors or energy levels of light that might be emitted as you jump back down. Which means that when you look at an emission spectrum, okay, that picture of all the light that's emitted, so this is different. The absorption spectrum, remember we shined white light through something and we just looked at the gaps. The emission spectrum, what you do is you take a gas of some kind and you excite all of the electrons in it somehow. The easiest way to do that is by heating them up. As you heat up those atoms, those electrons get that thermal energy, they actually bounce out to further orbitals that way as well. And then you look at the light that comes out of that thing as it cools down. In chemistry, when you did those splint tests or the flame tests, and you saw that earlier on the slide too as well, you see the colors. Those colors are caused by characteristic emissions based on the energy levels of the atoms that are being excited. So the emission spectrum looks just like the absorption spectrum. It has all the same lines, but it also has a bunch of more lines that happen at those like stop, gap, intermediate transitions as well. So the last topic in this already long video is photoelectricity and the photoelectric effect. So the question is, what happens if an electron that's in the ground state of an atom is hit by a photon, a very high energy photon that has 130 electron volts of energy? What's going to happen to it? Well, there's only 122.4 electron volts required to send this electron all the way to infinity, right? So we can absorb this because it's not going to leave me in between orbitals. That's not a problem. It's going to absorb that photon whole. We know that electron is going to be spit out here to infinity because we absorbed, enough energy to do that, 122.4. But there's some leftover energy. There's 7.6 extra volts or electron volts of energy. And so what happens is that electron takes that extra energy and turns it into kinetic energy, and that electron actually has some velocity and is moving as well. So this happens in the real world. If you have a sample of metal and you shine photons on it, what you'll see is electrons actually pop off of the metal. This is called the photoelectric effect. And this is the foundation of what we use solar panels for. So we have sun sending photons in, and those photons hit the electrons, and those electrons are actually pushed off the metal. And if you put them inside of a circuit, you can actually capture them and take that energy that the electrons have, this kinetic energy that they have, the extra energy. So we need a little bit of energy to kick them off the atom. Anything that's left over can turn into electrical energy that we can use in our circuit. So when you hear the photoelectric effect in any kind of problem, it's generally speaking going to be addressed with this equation right here, which is known as the photoelectric effect equation. And we use this equation to describe that process from the last slide, which is the process in which electrons are actually ejected from atoms through the absorption of high energy photons. So in this equation, the K max stands for the extra kinetic energy of the emitted photon. So it was that 7 point whatever electron volts from the last slide. It was the leftover energy equals the energy from the photon that was coming in minus something phi, which is in this case representing something called the work function. The word work function of an atom refers to the difference between the ground state energy level and the energy at infinity. So it's like the amount of energy required to ionize that electron in the first place. The work functions are material dependent, and so if they gave you a question like this on a test, they'd have to give you a table of work functions of selected metals or materials. So the work function basically tells me how much energy does an electron have to absorb to get kicked out of the atom. If I was to rewrite this equation, I would write it the other way. I would write HF equals work function plus K max, because that's how I tend to think of it. I tend to think of it as this is the energy coming in, and then what happens is this has to eject it. This is the amount of energy to eject, and then this is the leftover, which makes that electron go faster. This is the same equation, it's just slightly rearranged. A note, right, in our last material that we were looking at, it had a really, really high work function. So this is a material that is probably not likely to undergo the photoelectric effect because it takes a really, really high energy photon just to get that electron out of the atom. These metals and these materials have much lower work function. So these are things that are good candidates to use for making solar power or solar energy, because the atoms don't have to absorb that much energy before they get kicked out. There's a great lab that I will put a link to at some point in the PhET simulation series that talks about, lets you play around with changing the setup for a photoelectric effect. And so I'm just going to show you a few of the results of this lab. You can see we've got a light we can turn on. We can adjust the intensity, which is the brightness or the amplitude of the light, and we can also adjust the frequency or the color. This is a battery. I'm not going to play with it in this example, but it's a little bit relevant when it comes to real-world applications. So the idea is, and you can set up your target for different metals or materials, and changing that is going to change the work function, of course, of the electrons that you are trying to eject. So this first screenshot shows that if the energy of the light, based on the color, okay, so the color that I chose here, has less energy, so those photons, the HF of those photons is less than the work function of the metal, okay, that means we are not able to eject any electrons, right? In that energy level diagram, if we don't provide a light of a certain frequency, it doesn't provide enough energy to get it all the way out here. So we end up not ejecting. So in this case, this orange light is shining on this metal, and you'll notice there are no electrons being ejected because no single photon of that orange light has enough energy to kick it all the way out. And an electron can't, like, you know, obviously the total energy of this light is plenty because the total energy of the light is NHF, the number of photons times the energy of each photon. But an electron can't absorb multiple photons at a time. It can only absorb one at a time. So if the individual photons, if HF of the photons is less than the work function, we don't have any photoelectric effect happening. And that's why we see the current in this graph is 0. So let's move to another example where I have increased the frequency. So now we're not doing orange anymore. We increased the frequency to a green color, which is a higher energy frequency because green is a higher frequency. And so you'll notice now we have these little electrons being emitted, and they are bouncing across this gap and going through the circuit. So I have hit basically, this green is essentially exactly the bare minimum where I can start getting electrons off of the target. And if I continue to increase the frequency of the light, so I go from green up here to UV, what you'll see is that the energy of the emitted photons goes up. In other words, these guys have more Kmax, okay, than these ones do, because these ones have just enough energy to overcome that work function, right, and not a lot left over. As my light frequency goes up, okay, I don't eject any more electrons. I'm still kicking out about the same number of electrons every second because each photon, same number of photons, give or take, hitting this thing. But the difference is that each electron that's ejected has a lot more velocity and a lot more kinetic energy because there's spare, there's leftover energy beyond just accomplishing the ejection or hitting that work function. So the second experiment involves not changing the frequency, but instead changing the intensity of the light, which you remember is the amplitude or the number of light photons that are coming in. So we are at a frequency here that is beyond the work function, so we're ejecting some electrons. And what I'm going to do then is go from a low intensity up to a high intensity. So that means that I'm making this brighter light. So if you increase the intensity of the light, what happens is the number of electrons goes way up because each electron can only absorb individual photons. And so if this is sending in a lot more photons, that's a lot more opportunities to hit those electrons and eject them. So we have a much dramatic increase in current here as the intensity of the light went up. What doesn't change, however, is the kinetic energy of these things, okay, because they're getting whatever kinetic energy is provided by the frequency. So the Kmax is the same there and here. The difference is the number of electrons when we have more photons is higher, okay? So in these photoelectric effect experiments, you need to understand the equation, how it works, and you need to understand how would changing the frequency of light impact the current or the electrons that are ejected, and how would changing the intensity do something different. I think this is the last slide in this series. I know this is a big, long lecture, so please feel free to ask me questions if any of this was unclear. Thanks for watching. Just kidding, I actually have one more slide, which is a sample problem to be solved. So you might encounter a question on exam that says something like, calculate the maximum velocity a photoelectron would have when a sample of zinc is irradiated with 200 nanometer light. You would have to be given the work functions of those materials. So you can see that zinc is right there in the middle. And I would encourage you to pause the video and see if you can work through it. And if you get stuck, come back and listen to my steps and check the answer at the end. Okay, so the steps I would take. First thing, I would calculate the frequency of the 200 nanometer light. So we're going to be using our wave equation, wavelength equals c over f. I want to know the f of this thing, but you got to make sure that you use meters, not nanometers here. So 200 nanometers is 200 times 10 to the negative 9th meters in this calculation. The second step is going to be to calculate the energy of that photon of light. So once you've got that F, you are going to be using E equals HF, which is our Planck's frequency energy relationship. Remember to use realize that your solution is going to be in electron volts, because we want electron volts eventually to be using with our photoelectric effect equation. So I'm going to use the H constant that is in the units of electron volts. The third step is to use the photoelectric effect equation and the work function of zinc to figure out what the maximum Ke of a photoelectron would be. So I would solve Ke equals this HF value that I just calculated in electron volts minus the work function of zinc, which I would get from that table. So I should have kinetic energy. And then you need to take your kinetic energy that you got, which remember is going to be in electron volts because of all of this, and convert it back into joules. So you can find kinetic energy in joules. And there is that conversion from electron volts to joules that's on your equation sheet if you need it. And then the very last step is to calculate the velocity of the electron using the kinetic energy and the mass of the electron. So Ke is 1/2 mv squared. But to use this equation, this has to be in joules, okay, in order to get a velocity in meters every second. So that's why we had to do the conversion. This mass is given to you on an equation sheet. So that's a constant mass of an electron. And so the last unknown is the velocity, which you should be able to calculate in meters every second. The solution I got was 816,944 meters every second. That is realistic, and it's super crazy fast, just so you guys know. All right, that's the end of the video. Thanks for watching.